In my last lecture, we looked at what happens when an object rolls horizontally. We examined the dynamics of the situation. In that situation, the torque due to the normal force is important because it's ultimately that torque that causes the ball as it rolls horizontally across the desk. It's ultimately that torque that causes the rotation to slow down. You're not going to encounter a numerical example of any kind involving an object rolling horizontally, but you may encounter it qualitatively as a question on the AP exam or on an examination of some sort. So be aware of the situation. However, you may run across a numerical example of some sort if an object rolls downhill or if an object rolls uphill. So let's go ahead and turn those scenarios into a basic problem here. Let me go ahead and read it to you and then copy it down into your notes. Okay, an object of mass m and radius capital R rolls without slipping on an incline when an angle of inclination theta. So we're just going to do everything in terms of the symbols. That's fine. Find the acceleration if the object rolls first downhill and then uphill. We'll determine the accelerations for two objects. A sphere, like so, I'll use my tennis ball, and a hoop, like so, I'll use this tape roll. Okay, let's see what happens as one of these objects rolls downhill first. Okay, so object rolls downhill. Okay, let's draw out the situation. First of all, just draw out a basic incline like so. Where right here is the angle theta as always. Okay, here's our object, like so. Its rolling motion is in this direction. And of course, as it rolls downhill, it speeds up. So the acceleration vector is going to be downhill. This is an immediate difference between what happened earlier with an object rolling horizontally, which was slowing down as it did. In this case, of course, the object is going to speed up. Okay, right here is the center of mass, where once again we treat the axis of rotation, and then we just draw out our force diagram, add up everything using F equals ma, and we'll also draw out the torques as well. Okay, first of all, the force of gravity applied to the center of mass points straight downwards like so. Right down here is the force of static friction, like so. And then slightly ahead of the center of mass, due to the rolling motion and also due to the fact that the object is not perfectly rigid, remember it sags a little bit under its own weight. For these reasons, the normal force is slightly ahead of the center of mass. I'll draw it like this. Okay, let's go ahead and take mg and break it into its usual components in these types of problems, like so, where right here in green is the angle theta. And now let's add everything up by using F equals ma, where as always we think of the direction of the acceleration as the positive direction. So right here is mg sine theta in the same direction as A, and then minus the force of static friction, like so. This then gives us the net force, mass times acceleration. Okay, perpendicular to the incline, like so, you have the normal force canceling out the mg cosine theta, like so. And then taking a look particularly at this expression here, think of it thus far as one equation and two unknowns. The two unknowns are the acceleration that we're trying to find and the force of static friction. So then therefore I need another equation. This obviously comes from examining the torques. Okay, now there is no torque exerted upon the object due to gravity. And the reason for that is because there is no R, there is no moment arm in R cross F, because the force of gravity is applied at the center of mass, the axis of rotation. So as always, there's no torque due to gravity. However, there is going to be a torque due to static friction and also a torque due to the normal force. We've got to get the directions straight as we write this out. So let's take a look at, first of all, the force of static friction. So right here is a moment arm, which is equal to the radius of the ball or the hoop, like so. And then right here is the force of static friction pointing uphill. There's a 90-degree angle between the two. So now do R cross F. So when I go R cross F like so, that gives me a torque vector into the board. So right here is my torque vector like so. But when I do R cross F, notice the direction that my fingers are curling. My fingers are curling in the direction of the acceleration. So because of that, then we have to think of this torque as a positive number. This torque is going to be R times Fs. Okay, notice immediately also that this is different from what happened earlier in the horizontal situation where that torque was negative. In this case, this torque, yes, is speeding up the rotation of the ball. It is accelerating in that direction, therefore that's a positive torque. Okay, now let's take a look at the torque due to the normal force. So right here is the moment arm associated with the normal force. Kind of looks something like this. Where then right here is the normal force like so, and then here's the angle phi. So now when you go R cross F here, you get a torque that's out of the board. Notice the direction of my fingers curling, however, is opposite of the acceleration A. We then therefore have to think of this torque as a negative number. So that torque points out of the board like so, tau sub n, and we have to think of it as a negative number. So then here's what happens when we add up the torques. So I have R times F sub s minus the torque due to the normal force is equal to I times alpha. Okay, alpha, because the object is rolling without slipping, is A over R. Let's go ahead and write that in here. So, okay, and then what do we do at this point? Well, unlike the situation earlier, which was horizontal and the acceleration was a small number, here in this case, when an object rolls downhill, the acceleration is a large number. In other words, this number here is large compared to this number here. This number here is small because the angle phi is in fact pretty close to 180 degrees. In this situation, therefore, we can neglect the torque due to the normal force. You can't do that, however, in the horizontal situation because it is that torque that slows down the ball. In this case, however, we can neglect it. The reason why it's negligible is because the torque due to static friction is so much larger than this number because the acceleration is a fairly large number. So we just set this equal to 0 for that reason. Okay, now let me do a little bit of erasing here and I'll start to combine the equations together. So let's get rid of the stuff we don't need. Like so. Okay, and now what I do is I take this expression here and I solve it for the force of static friction. So let me clean it up a little bit first. There we go, like so. Let me go ahead and take the expression now and solve it for the force of static friction. Okay, so just divide the R to the other side and the force of static friction, and therefore is this expression here. And then we take this expression for the force of static friction, plug it into there, and then solve for the acceleration A. Okay, so mg sine theta, and then minus the force of static friction equals ma. Move this term to the other side. Do a little bit of factoring here as we go, like this. And then divide the parentheses then to the denominator to the other side to get the acceleration A by itself. Okay, that then gives us this. Like so. Okay, so now let's go ahead and apply this basic expression that I've derived here for the hoop and the sphere. So let's call this A and B. Let's say the hoop first. Okay, ICM for the hoop, if you remember, of course, is mr squared. So let's go ahead and plug that into here, that is. When I do, the r squareds will cancel out, and then I get m plus m for a total of 2m in the denominator. But let me go ahead and do this a little bit more carefully. There we go. Like so. So as I was saying, the r squareds cancel. You get 2m in the denominator, and then m divided by 2m is 1/2. We end up with an acceleration here of 1/2 g sine theta, like so. Okay, then let's see what happens with a sphere, a ball. We'll call this B. Okay, ICM for the sphere is 2/5 mr squared. Okay, let's go ahead and plug that in here in the denominator of our basic expression. Okay, so the acceleration is mg sine theta, and then divided by m plus 2/5 mr squared over r squared, like so. So the r squareds here cancel out, and then you have, let's see, 5/5 plus 2/5 is 7/5 m. The m's cancel out, do a little bit of math, and this is 5/7 g sine theta, like so. Okay, so notice that the acceleration of the sphere is a little bit larger than that of the hoop. So then therefore I can show that by taking my two objects, setting them on an incline and releasing the objects from rest. We should find that the sphere, for example, which has a slightly larger acceleration, reaches the bottom of the incline first, as opposed to the hoop. This, of course, is assuming that I do this correctly. That is, I release the objects from rest at the same height than above the desk. So let me go ahead and do that like this. So let's set up an incline like so. There we go. And then I'll take the two objects here, set them onto the incline, let go of them at the same time. And lo and behold, the tennis ball did in fact reach the bottom of the ramp first. Okay, now compare the accelerations of these two objects to an acceleration that's just undergoing a translation without friction. For an object like so, that is undergoing a translation without friction, recall Galileo's experimental result that the acceleration of such an object is just g sine theta, which is a bigger number than these numbers here. The reason for that has to do with conservation of energy. When an object rolls downhill, its initial potential energy is not just becoming its translational kinetic energy, as it would be for an object just sliding downhill and undergoing a translation. Instead, some of the potential energy is transforming into rotational kinetic energy. We'll get to that a little bit later on. Okay, now this was for the situations involving objects rolling downhill. Let's now see what happens when they roll uphill. All right, so I'll derive it from scratch. Okay, so objects rolling uphill. Okay, once again, draw it out first, however. So here's our incline, angle theta. Here's our object, like so. In this case, the rolling motion is like this. But of course, the object is slowing down, so the acceleration vector points like this. Okay, and then we've got our forces. Once again, here's the center of mass, the axis of rotation. So right here is the force of gravity, mg straight downwards. Right here is the force of static friction in the same direction as A, like an object rolling horizontally. And then slightly ahead of the center of mass, let me redraw this. Slightly ahead of the center of mass in the direction of the rolling motion is the normal force like so. Once again, the object is not perfectly rigid. It sags a little bit under its own weight. Okay, take mg and break it into its usual components like so, here and here, where here is the angle theta. And now we'll add up the forces first of all. So I have mg sine theta in the same direction as A, so I still think of that as a positive force, but now plus the force of static friction in the same direction as A. So mg sine theta plus Fs equals ma. And then perpendicular to the incline, you have the normal force, once again canceling out mg cosine theta. So, and now let's take a look at the torques, and then once again, we gotta be really careful about positive signs and negative signs. So there's no torque due to gravity, as always. There's no R in R cross F. But now let's take a look at the torque due to the force of static friction. So right there is the moment arm, capital R, like so. Here's the force of static friction pointing downhill. Here's the right angle between those two vectors. And now we'll go ahead and do R cross F. So watch this. R cross F gives me a torque vector that's out of the board. All right, so there's that torque vector like so. But now if I go R cross F and I curl my fingers like that, notice that my right hand fingers are curling in the direction opposite of the acceleration. So then therefore, yes, we have to think of this torque as a negative number, just like we did for the horizontal situation. So this torque is minus RFS for that reason. Okay, now let's take a look at the normal force. So right here is the moment arm like so. Kind of like that. Right there is the normal force like that. And then here's the angle between them. Here's the angle phi, very nearly equal to 180 degrees. Let's go ahead and do R cross F here. Okay, so R cross F gives you a torque vector into the board. Notice that that's in the same direction as the acceleration A in the sense of how my right hand fingers are curling. Therefore, we have to think of this torque as positive, just like we did in the horizontal case. Like so. So once again, R cross F, like so, is into the board. So here's that torque vector into the board, and now we'll add up the torques. So this positive torque plus that negative torque, this then gives us I times alpha, like so. Okay, once again, we replace the alpha with A over R. I'm going to do some erasing here at this point, by the way, so let me go ahead and do that. Okay, so tau n minus RFS equals I times A over R for a rolling object. And then you get to this point, you say, okay, well, now what? Well, once again, on the diagram that I just erased, the angle phi for the torque due to the normal force is pretty close to 180 degrees. So the sine of that angle is pretty close to 0. This allows us to, yes, mathematically say that this number here is negligible. But when I do, it starts to look like I'm contradicting myself once again, like I did in the horizontal case. In the horizontal case, however, you cannot consider this to be negligible. Here you can, and the reason why is because once again, the acceleration is a large number. The object slows down really quickly when it rolls downhill. Watch what happens now just in terms of the math. So what I'm going to do is take this expression here and solve it for the force of static friction. So move this negative r down to the denominator on the other side like so. And then take this expression and plug it into here, where that's a positive. So now I've got mg sine theta plus fs. So then therefore it's this like so, equals ma. And now at this point the problem is identical to what we saw earlier with the object rolling downhill. So now I'm going to move this term to the other side and do some factoring as I go. That is like so. There it is like that. And then we'll go ahead and divide by the parentheses now to get the acceleration A. Okay, and then when I do, I end up with the exact same expression as I did before for the situation involving objects rolling downhill. So then therefore, if you plug in what happens for the hoop, you get the same acceleration as before, 1/2 g sine theta. If we do this then for the sphere, you get the same acceleration as before, 5/7 g sine theta. Here's how I kind of talk my way through understanding why we can neglect the normal force, the torque due to the normal force in this situation, whereas we couldn't do that in the horizontal situation. I just like to think of it in terms of conservation of energy. The acceleration of the objects rolling downhill and uphill has to be the same number, because if they weren't the same number, this would then imply that there's some energy either destroyed or created in one situation or the other to give you a different result. So then therefore, if you have an object that's rolling downhill, the potential energy transforms into translational and rotational kinetic energy, and then vice versa for an object rolling uphill. An object rolling uphill has to transform back into potential energy, and it has to be basically the same value as before. If it wasn't, that would violate conservation of energy. Some energy would have been created or destroyed if these accelerations were different for an object rolling uphill as opposed to downhill. That's the easiest way to think of what is happening here in terms of the dynamics.